Okay, we are going to talk about limits, section 2.2. So she says that limits were kind of made by this person and this person but we want to talk about limits in this context. So hopefully you have studied limits in the context of a single variable, in this single input variable in this case, and you've seen this notation, which says that as the input gets closer and closer to some place, if the output gets closer and closer to some other place, we say that that's the limit as x approaches a. And a little bit more richer understanding of that statement is, it's still an imprecise understanding of that statement is, means that you can make the numerical value of f, the output of f, arbitrarily close to L, so as close as L to L as you want, by keeping x sufficiently close but not equal to a. So with that idea of limit, we can generalize it to a function like this, and we'll write something like this, compare with this. So what we're, and this is a vector, and this is a vector. And we're saying that we can get as close, we can get as close to a given output L in this space. We can get as close to that as we want because because f goes into this space, or its output is in this space. So we're getting an output in that space, so we can get as close to a vector L in that space as we want by choosing our vector x, the input, to be arbitrarily close to here. In that case, we write this. In that case, we write that the limit of f as x approaches a is equal to L, and these are all bold. They say that they talk about the limit vector L. It's the limit L, or since L is a vector, the limit vector L. Now we've been using the word close, and that means the distance between, so f can get close to L, means that the distance between f and L is small. So we need, when we're just talking about this, we know what we mean by distance, but what do we have to be clear about what we mean by distance when we're talking about vector f and L? So, but fortunately we already have a concept of distance in Rm or Rn, and the concept of distance is we use the norm of the difference between these two. So the norm has been generalized to Rm, so we can talk about this is in Rm and this is in Rm. They're both this is in Rm and this is in Rm. So they're both in Rm. We can subtract them. We get a vector, and remember that's like the displacement vector, which is basically the distance between the two tips, which is what we mean by the distance. And but it's in Rm, so there are no tips, so to speak. But anyway, we can do that and and we can apply it this norm. We have this operation we can do. So it's just the dot product, square rooted. So now we can be precise about what we mean by this, or preciser. So we mean that we can, when this is sufficiently close to a, when x is sufficiently close to a, again using using the norm, then this will be close to L. And just to reemphasize, when we're talking about, so if we have a scalar valued output, then this will be the absolute value. This will still be the like this. And if we have just a function of one variable, then this would be replaced by this. Just reviewing the concept of a limit from R to R. Okay, so suppose we had this function here, which looks like this. And so they're going to ask what is the limit at 1? At 1, so here. So as we get closer and closer to 1, what is the limit? Now you may recall that this won't have a limit because we have to get, what does it say? The limit can't be 0. You might guess it's 0 because no matter how near we make x to 1, we get, so no matter how small, no matter how close we make x to 1, so we're trying to get close, know what's happening near 1. So as close as we get to 1, that is, when we make x minus 1 small, that means x is close to 1, the absolute value of it, then we're still talking about x close to 1 means could be here or could be here. That's the point. X could be here or here, even though it's very close to 1. Then you can't say that the limit is 0, because when you're over here for x, the height is always going to be 2. So the distance between this and this is always going to be 2. Why is it between 0? Because on this side it's going to be so we're wondering if we can make it as close to 0 as possible, the output, but we can't. The height is always going to be 2, or the difference is always going to be 2 between 0 and any point just to the left of 1. And similarly for the right. So there is no limit. The limit does not exist for this function. So we have to remember that there are cases where the limit doesn't exist. So next example is when we have take an example from R2 to R2 and take this example. So 5x is the function. And they say it should be intuitively obvious that the limit as x approaches I plus j, so that this is a vector, as x approaches that vector, we're talking about the limit of this function is 5x, so we just replace 5x, and they're saying it should be obvious that this is going to be the answer. On the other hand, if we want to prove it, what we have to say is, first of all, we say that x is equal to that, and then we want to say what is the distance between what we claim is the limit, which we claim the limit is here, and f of x. And so we write that out, and the distance can be rewritten like that because f of x looks like that. And then we can rewrite it like this, and we can rewrite, and then we have the norms, we can rewrite it like that. And then we can pull out a 5, and we get this. And then they say we can make this as small as we want as long as we make this quantity, which is what we need to do. We need to say that this, as long as this is sufficiently close to this, so as long as we make that quantity, the distance between them, small, because this is equal to this, but that's the same thing that we had here. So if we make this small, we can make this small. And we can make this as small as we want by making this small enough to make this as small as we want, because they're basically the same function. One is just 5 times the other. So if you don't quite get what we just did, you have to go back and read this 2 or 3 times, or maybe more, but just make sure you get the idea. Now we kind of generalize that same problem that we just did, the same example. We just go from Rn to Rn now. And we have, instead of 5, we have 3. We still get this kind of result. And you can read through it. And here's the, I thought that was n already. Oh, now we generalize it to this function, and we get this. Now, she says the main difficulty with this definition that we're using is in the terms arbitrarily small and sufficiently small. They are simply too vague. We can add some precision to our intuition as follows. Think of applying the function as, think of applying this function as performing some kind of scientific experiment. Letting the variable x take on a particular value in x amounts to, here, letting the variable x take on a particular value in x amounts to making certain measurements of the input variables to the experiment, and the resulting f of x can be considered to be the outcome of the experiment. So she's saying basically that like when you're evaluating f, you think of it as an experiment where you put in certain x's, and the outcome of the experiment is what you get out of the experiment. Experiments are designed to test theories, so suppose that this hypothetical experiment is designed to test the theory that that as the input is closer and closer to A, this A here, as this input is closer and closer to A, then the output gets closer and closer to L. So is it really true that as we get closer to A, the output actually gets closer to L? To verify this theory, you should establish some acceptable absolute experimental error for the outcome, say 5%. That is, we want to be able to get f of x to be as close to L by as close to, let's say we mean by 5 to within this amount, less than 0.05, if x minus a is sufficiently small. So if the distance between x and, if you're allowed to make x as small as close to a as you want, can you then make sure that f is within this range of L? That's the way she's writing this. Then just how small does this need to be? Perhaps it turns out that you must have x this close to a, and that if you do take x this close to a, then this will always be within this range. Does this mean that your theory is correct? Not yet. Now suppose you decide to be more exacting and will only accept an experimental error of 0.005 instead of 0.05. In other words, you desire that this be this close to L, that f be this close to L, that f be this close to L. Perhaps you find that if you take x close enough to A, this close to A, then this new goal can be achieved. Is your theory correct? Well, there's nothing sacred about this number, so perhaps you should insist that it be this number, that it has to be that close, or that it will be this number. The point is that if your theory is really correct, then no matter what absolute error, epsilon they call it now, you choose for your outcome, you should be able to find a tolerance level delta for your input x, so that if x is within delta of A, then f is within epsilon of L. It is this heuristic approach that motivates the technical definition of the limit. So here's the not intuitive definition, but the rigorous definition of the limit. So, so we have our function from Rn to Rm. What do we mean by the limit? Then to say that the limit as x approaches a of f equals L means that given any epsilon greater than 0, and that's the, what did they call that? That wasn't the tolerance. That was called the experimental error that was being applied to this part. Delta was being applied to this part. So anyway, given any experimental error epsilon greater than 0, we can find a tolerance delta, which will in general depend on epsilon, such that if epsilon, if x is in x, in here, and this is less than that and not equal to 0, so we're not worrying about when x actually equals a. That doesn't, we don't need that. If we put an equal sign here, that would be more of a condition, not less of a condition. So that by doing this, it's less of a condition. Then, or less strong of a condition, then this will be within epsilon. So this part here simply means that we care only about values f of x when x is near a, but not at a. So we don't care what happens at a. That doesn't affect whether, if it's not, if it at a it's something else or does something crazy, we don't care. All we want to say is what's happening when x is near a, can we make it within our tolerance? Not, it doesn't have to be that when x is equal to a. Okay, definition 2.2 is not easy to use in practice, and we won't use it frequently. Moreover, it is of little value insofar as it as actually evaluating limits of functions is concerned. The evaluation task limit of a function is more than more than one variable is in general a difficult task. So but they actually do it here. So let's see, what's this function? This is input of, so this is R3 as the input space and R1 as the output space. So I'm not going to go through this, but they do it. So you can go through that. Okay, so it would be good to read that just to see an example. And then they say that here's a more generalized version of the one that they just did. This one they just did was what? For this polynomial in 3 variables, actually it's a linear function in 3 variables, not just, and this is a linear function in n variables, and you get this kind of same result. So the idea is that for this kind of simple function, linear function, in n variables, and this is the output space is R, then as x gets closer to b, this thing will basically says you can just put in, for the limit, you can just put in b1, b2, b3, where, you know, b consists of b1, comma b2, comma b3, and so on. So you're allowed to just drop those in. So this limit problem is very easy to do, and we showed how to do it. We showed that it was true in this case, and to show it in the more general case below is similar to showing that it's true in this case. So we're going to actually just accept that this is true. So whenever we have a linear function like this, and we want to do as x approaches b, we can just drop b into the answer.